So today I'm going to talk about DAGs and BFTs, and basically the goal or my purpose is actually convince you that that's pretty much a solved problem, the consensus problem, and at least in the blockchain setting. So if you are focused on crypto, you should keep focusing on crypto. So, but yeah, let me try to convince you. So this is the general architecture of like a blockchain today, a monolithic blockchain today. Basically, there are three main components. You have the consensus, you hold the blocks of transactions. Then you have the execution, you execute these blocks. And then you need to persist it in storage. So basically, the main component, there are a few more, and you need to link between them, but that's basically the main component. And if you have a modern architecture of a blockchain, then you can actually execute everything in pipeline. Like if you can execute one block number I and already order block number I plus 1, and block number I minus 1 is now committed to storage, right? So you can have a pipeline architecture. And in this world, the overall throughput of your blockchain is going to be dominated by the throughput of the worst component over here, right? And today I'm going to focus on consensus, as like I said, I'm gonna try to prove you that consensus is no longer a bottleneck in this pipeline architecture. Okay, so to give some credit, this is all I want to present you today is a joint work with my co-authors, and also not on the slide, by the engineering team at Aptos that actually taught me the real difference between the old. But what I wanted to say is the real meaning of the word practical. Because what I believe is practical, it's not really practical. Okay, so just in general, this is like our work. We're working on it for a few years. Like we had a few papers where we this whole DAG-based approach. We started from POTSI, where we published the theory of how to use the DAGs. Then Narvel is the system of how to build the DAG. And Bullshark is basically, I'm going to talk about Bullshark today. We had a fast path, asynchronous, partially synchronous path to Bullshark. And what is not on this slide, but I do want to mention, is that I want to give some credit to Aleph. I know there are some people there from Aleph. Yeah, hey, Aleph, yeah. So Aleph is here, somewhere here, just before. All you need is DAG. There is Aleph, very cool paper. Unfortunately, I think what's the word there? Underrated, I mean. I think somehow lost in the literature. And we accidentally found it 1 week before the deadline. Oh, really? Whoa, somebody already did something very similar. But yeah, very cool paper. Okay, so let me go into the goal of what we're doing here. Remember consensus, and consensus has many flames and shapes, and we had the Rafael explaining to us all the models and everything. But I don't want to go into all these formal definition. Just on a very intuitive level, what we want to do is that we have the validators. We have n of them because we are in the permission world. We are building a permission blockchain. We are in a permission world. We have n validators. At most n, 1/3 of them can be Byzantine, and each of the validators gets a stream of transactions. They exchange a few messages, depends on the protocol that they're running, and then they're gonna the goal is for them to agree on a sequence of these transactions, right? That's basically the goal. We can add properties validity, agreement, termination, but that's basically what we're doing here, right? Okay, and the challenges, we have a few challenges. So we have a performance challenge. We want to do it, we want to support the maximum throughput that we can, in terms of the number of transactions we can order per second. We want to do it as fast as possible, latency. We want to be scalable in terms of the number of validators. We are here, we want to build something decentralized, right? So the more validators the system can have is the better. And I'm going to argue that simplicity is crucial and very, very important. Everything has to be very, very simple. Otherwise, you cannot deploy, you cannot maintain, you cannot debug. Okay, so it brings me to my agenda. I'm going to first talk about Narvel and how we scale the blockchain, and then I'm going to talk about Bullshark, and I'm going to claim, in my very, very objective opinion, or subjective, never mind, that is the simplest protocol out there. But it's very, very objective, right? Yeah. Okay, so let's start with how to scale consensus. So if you think about the current design, most of the protocols in the literature, they have this metric of message complexity. And the goal over the years was to improve the message complexity, like less and less messages. And not only messages, you only have the bit complexity, less bits sent on the network. This was the literature, this was the goal of many theoretical papers for years. And this is very, very nice, but one thing is that we need to remember is that the data has to be shared. Like, we cannot go around it, the data has to be shared. In order to execute the transaction, I need to have them, right? So if we look on existing protocols, these monolithic protocols, SBFT, PBFT, Tendermint / hot stuff, everything, all the partial synchronous one at least, they all assume a leader, and the leader is sending the data and keep sending the data and keep sending the data, and the rest, like this is how a typical consensus works. Like, you have the leader sends the data, the rest doing very minor stuff. They just sign it, make sure that they double sign, and then send it back. The leader again send the data. So if we look on the research utilization graph, the leader works a lot, and the rest of the replicas are mostly idle. So not surprisingly, the overall performance of the system is going to be bottlenecked by the ability of the leader to transfer data. And we want something that looks more like this, more load balanced, right? Like, we can have a leader, but we want the research utilization to be balanced. Everybody works slightly, the rest works slightly more. The leader works a lot less, and this way we can really utilize the system and make it achieve the performance that the hardware can actually give us. Okay, so this brings me to the key observation in the novel paper, which is the coupling data dissemination from metadata is the key to achieve performance and scalability. So we are going to have the validators to disseminate data, and we are going to have the validators to order metadata, just metadata only. And that's going to be two separate protocols that are going to be connected to each other, but we are not going to mix the two. Okay? The leader is no longer going to send this huge amount of data. And so the way it's going to look like is that each validator asynchronously disseminate data, and they all do it together. Right? And if you look at the graph of the research utilization, clearly it looks like this, because they all just keep sending data, and they all do it, and they all do the same. So one more. So how is it actually going to work? So Lara gave a beautiful presentation about proof of availability and how we can use erasure codes and other techniques to improve it. But for our specific use case, we can do something like extremely simple. We don't need this. All we need to do is for a sender here. Okay, this is something, if you're familiar, very close to consistent broadcast, or at least for the first part of it. So if you have a sender, the sender sends the data to everybody else. They sign it and send back the signature. And by the signature, they basically say, I promised you I'm going to persist the data, I'm going to store it until you tell me otherwise. So in practice, the data will have an expiration time, and they are going to promise that they are going to keep it until the expiration time. So then the sender will collect a quorum certificate. You need to wait for enough replies. In this world, n-f replies, and you will get a quorum certificate. Now, this quorum certificate will guarantee that if I show you this quorum certificate, if you will know, even though now you don't have the data, but you know that enough honest guys here, enough honest validators here promise to store the data, so if I need the data in the future and I have the quorum certificate, I can always get it. Okay, so for example, I come to execute something, I don't have the data, I have a quorum certificate, I check who signed it, and I go and I ask them, and some will reply. Some are Byzantine, okay, we can't do anything about them, but there will be enough honest here that will reply with the data. Okay, and so I told you before that, okay, let's go back. So here, actually, Lara explained to us how we can make this more efficient, because the leader here is a bottleneck, clearly a bottleneck. Not the leader, sorry, it's not the leader. The sender here is clearly a bottleneck because he's sending the data and the rest just sign, and I just told you 5 slides ago that this is bad, right? And we can improve it with erasure codes technique and stuff like this, but in our case, we really don't need to because like I said before, everybody are doing the same thing. All the validators are gonna run the same protocol to disseminate data, so at the end of the day, it's gonna be perfectly load balanced. They all will keep sending data. And that's an important point. Okay, so another very cool thing about this architecture is like it's very easy to scale out. And what I mean by that is that before, like as I explained it, where a validator is a single machine, okay, sends data. Now we can easily turn this validator to a cluster, have several machines. Each machine can send data, right? And it's completely like orthogonal. They just send data, gets this proof of availability certificates, right? So we can perfectly parallelize it. We have throw more machine on it. We disseminate more data. As simple as that. And this is a graph from the Narvel paper. Where we show that if we have more we call it workers in the paper, if we have more machines per validator, we can actually scale linearly the throughput of the entire consensus. So it's actually this architecture is very easily scaled if you throw more hardware on it. Okay. Okay, so now let's talk about metadata ordering. So we disseminate the data, we get this proof of availabilities, how are we gonna order it? So yes, so we are gonna still use consensus, our favorite consensus, right? You can pick whatever you want, but this time the consensus, the leader is gonna just send this metadata. So the metadata is very small, it's just a certificate, right? So if you look at this like resource utilization graph, it's almost perfect, right? The leader doing slightly more work because he needs to send these certificates. We will get to a perfect graph today, but this is like already almost perfect. And the thing is that the leader is no longer the bottleneck, and then given that, consensus communication complexity is much less important now because it's no longer these huge messages, so we don't really care if we pay linear, almost linear. So what we do care about is latency. So if there is a trade-off between latency and message complexity, just in case of, for example, hot stuff, right? It gives you this extra round in order to try to achieve linear communication, and compared to PBFT, for example, in which the view change is actually quadratic, but you have one less round. So probably better to pick PBFT because in terms of throughput, it's not going to harm you, but you're going to win a lot in latency, like 33% for latency. Yeah, one more, of course. Yes, so quorum store, this is like I want to share some engineering experience that I had. So quorum store is how we call the Narwhal implementation inside Aptos. And the consensus that we are using is Jolteon, which is exactly what I described before. It has the pipeline property of hot stuff, but we go back to the PBFT view change in order to win the latency because we don't really care too much about this linearity anymore. And we run a consensus-only test, and with like over 100 validators, 3 regions set up. Yeah, the numbers are not finalized, so I don't want to share it because we're still like playing with configs and like trying to achieve the best numbers we can, and we're going to publish it soon. But it gives us like at least 10x performance throughput on top of just running this Jolteon protocol alone, like where the leader sends the data. This simple trick of like disseminating the data asynchronously and the leader simply said the certificate gave us 10x throughput in consensus-only tests. And one very cool and surprising thing, at least for me, is that we actually was able to improve the latency as well. And this was very counterintuitive to me because before we just had the consensus. Now we had another round trip before the consensus, right? Because we need to achieve this, to get this proof of availability. So I was ready to sacrifice some latency to gain throughput. But it turns out that the end-to-end latency is actually better. And when we thought about it, it makes sense because now the reader does not send this huge amount of data anymore, so the consensus itself is much faster, right? The steps of the consensus is becoming much faster, so the all-to-all actually improved. It was very, very surprising to me. Okay, so now I wanna make a note here that production code is complex, and what I wanna so this is just I don't know, that's not very important. Just like a figure of how how it looks in our design doc, this simple protocol that I can describe in 4 lines. You send to everybody, they sign, they send it back to me, I have the certificate, that's it, right? What we call quorum store, the novel implementation, very easy, less than 10 lines of pseudocode, ends up in this design doc. And when we actually implement it, we need to think about storage, because we persist stuff. Because we have storage, we need to think about cache, because we want to be efficiently read stuff from storage, right? Then we need to think about quota, because we don't want Byzantine validators to pollute our storage, right, and run out of storage. So we need quotas. We need expiration and garbage collection, or we'll be able to clean our storage. We need to be able to state sync, because if somebody is behind, it needs to state sync, right? And network prioritization, because we need to, some messages are more important than the other. For example, disseminating the data is less important than getting back the proofs and aggregate it to a quorum certificate, right? So we need to prioritize the network. We need to back pressure, because now the consensus is so fast, it's no longer the data lag, but if we let it run freely, so that it will it will kill the rest of the system, because execution and storage cannot keep up, right? So we need to implement back pressure, and etc., 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 and of course we need to maintain and debug all of this, right? So my point here is just this simple 10 lines of pseudocode ended up in quite complex system, like a few thousand lines of code easily, without even like tests, right? So, and this is, for me, perfect way to move to the second part of the talk, in which I'm going to claim that simplicity is important, because you see, simple code, simple production, simple pseudocode, simple production code, complicated pseudocode, impossible production code. And yes, so I will pause for a second and ask if there is a question on the first part before I move to the second part. Okay, no question. Yeah, I think it's so simple, so you just understood everything. Okay, so next I'm going to talk about the DAG approach to solve BFT. And as I said, I mean, the DAG approach introduced even before Aleph, there was previous works. I'm not going to touch them. There was the hash graph and some others. But I think Aleph was the first to introduce a round-based DAG, and I'm going to explain in a second what does it mean, a round-based DAG. And I'm going to also focus on round-based DAGs. and for me, a DAG is a network abstraction. This is what it is, a network abstraction. So you need to build a system. That's true, and systems are complex, right? But you need to do it once. You build a DAG, you build your system, you debug, you do everything you need, you have a running system, you can trust it, you have a DAG. And then on top of this DAG, it actually abstracts all your network. You don't need to do anything else. This is what I'm claiming here today, because you can piggyback every protocol you want on top of the DAG. Take your favorite crypto protocol, ADKG, MPC, whatever you want, you can piggyback on top of the DAG. The system itself is like perfectly load balanced because it's leaderless, as I shortly explain. And the most cool part of it is that once you have a DAG, you can solve consensus, you can order all these nodes here on the DAG with zero communication overhead, nothing. You look at the DAG, you order it, that's it. You don't need the view change, you don't need the view synchronization, and Rafael talked a little bit about it, and like for any of you who are familiar with these protocols, all the details, all the complexity, they're always hidden inside this view change, view synchronization mechanism, and sometimes they're even missing from the papers. So you don't need any of it. And another cool thing that I really like about it, that and I will explain, it has a very easy way to switch between partial synchrony to asynchrony. Right? That's very simple. One day, if you want, you just need to build the DAG, and then you can decide which one you want, and you can like change on the fly. You don't need to to build your own consensus. One day you understand that asynchrony is important because you're like under attack half of the time. Okay, so let's talk about building the DAG. So as I said before, our DAG is going to be a round-based DAG. So it means that we advance in rounds, and it means that in each round, each validator has an opportunity to have one node to the DAG. Okay, so this is how we're going to build it. This is a view from, this is the point of view of validator 4. Okay, just I randomly pick validator 4, and this is how validator 4 is going to build the DAG. And so different validators might have slightly different view of the DAG because of the asynchronous communication, and this is how validator 4 is going to see it. So at the beginning, we have this Genesis nodes, okay? Easy. Like in the real blockchain, we have the Genesis block. Here, we were going to have Genesis nodes for round 1. Now our validator 4, prepare a new node. what he needs to do is to link to n minus f nodes in the previous round. Okay, so he links, he adds like n minus f links to the previous round. In addition, because we are gonna solve consensus, right? So he adds like the proof of availabilities that we know already how he obtained them, right? There's a separate mechanism to get proof of availabilities, and he's gonna add this proof of availabilities to the DAG. And as I told you before, we can piggyback any other application. So every data, metadata from other application, you can just piggyback and add to the node. Now this node is going to broadcast to all other validators, and all the other validators are going to do the same. So so this node, our validator, validator 4, I'm sometimes confuse node and validator. It's very, very confusing. Yeah, I'm sorry. Yeah. So this validator, validator 4, is going to wait now for n minus f nodes to be delivered to him by other validators. And once their delivery is ready to move another round, this is a round-based DAG. So now he's continuing doing the same. He links to n minus f nodes in the previous round. He prepares a new node, add proof of availability, add the metadata from like other application, and so on and so forth. This is how we build the DAG. So any questions about how we build the DAG? Like at least the pseudocode is very simple. All right. So we do have a few challenges here when we come to build it. So first is reliable communication. So as I told you, in order to advance round, in order to prepare a new node and broadcast it, I need to link to n minus f nodes in the previous round. So I need to have them. So f validators might be Byzantine. In this case, this is actually doing his job. But f validators might be Byzantine, never send me nothing, right? And the other n minus f, I need to receive all their nodes. And for that, I need reliable communication. I need to know that if an honest guy sends me the node, I will eventually get it. So we need to implement some mechanism for retransmit stuff and like ACKs and just to make sure it works. Okay, the other important thing is the causal history. So if I add a node to the DAG, I have all its causal history. So causal history of the DAG is everything that's linked to this node, right? So I will not add a node to the DAG unless I have all the causal history in the DAG. So I also need to take care of this when I build the DAG. And the last and probably the most important one is non-equivocation. So if I have a node and another validator also have a node, say we both have the node of validator 4 and round 4, so this node is identical. So even a Byzantine guy cannot lie about this node. This node is going to be exactly the same. It will have exactly the same edges, and it will have exactly the same metadata. Everything is going to be the same. And there are a few ways to achieve it. One way is to just broadcast via a reliable broadcast channel, right? It's going to give it to you, some reliable broadcast protocol that's going to give you these properties. But we are doing something much more simpler, is simply when we want to broadcast the node, we are going to broadcast the header and to send the header to everybody else. All the other validators are going to sign it. Before signing it, they are going to check whether they already signed something for me in this round. If they do, then I am trying to equivocate they are not going to sign. But if I didn't, they are going to sign and send me back the signature. I'm going to collect the certificate, and I'm going to send this certificate again, and this is basically my round. So each node in a round also have a certificate to prove non-equivocation. Okay, so with this in mind, this is how we build the DAG. There are the properties of the DAG. And now I want to explain to you the magic. So we have the DAG, and from this, we get this. Completely total order, and if you remember the goal, this is exactly the goal. We're going to order all the transaction, right? So from this, we get this. And the magic here is that we have zero communication overhead. We are not going to send any more messages. Like each validator, we are building the DAG, right? Each validator has its own view of the DAG, is going to look at it and going to say, okay, that's the order. And they're all going to agree on it without any more messages. So yeah, this is like I said, started with Aleph, and then this other follow-up works did basically the same idea, some slightly different properties. So, and then I want to focus on Bullshark today for one reason. it's the simplest protocol, so I can actually explain it in the remaining time that I have, and the rest, it's like once you get the general idea, all the rest you can figure out very easily. Even the Bullshark has a few variants, so there is the partial synchrony version, which I'm going to focus on. It's the simplest one. There is the asynchronous version, just some variant of the DAG right there, and the full Bullshark is actually best of both worlds. It's try the fast path, and if it doesn't work, it will like fall back to the asynchronous version. I'm going to focus on the partial synchronous version. Okay, so let's go, let's do it. So again, I want to mention again non-equivocation because this is crucial. We need to understand that Byzantine validators cannot do anything. They cannot lie. They simply cannot lie. We just eliminate this ability of them by this mechanism to make the certificates of the nodes, right? They cannot lie. So the point is that it's possible because the network is asynchronous and validator 4 already have this node, and validator 1 doesn't have it yet. But if they both have the, if they both have the same node, it's going to be exactly the same node, exactly the same edges, exactly the same metadata, and by applying the same argument, like recursively, the entire causal history is going to be the same, right? That's a property of the DAG that we have. Okay. So now the goal, we have the DAG, we want to order it, and we're going to order it by interpreting the nodes of the DAG and the edges of the DAG. So in every, what is this? This is odd or even? Let's say this is, this is odd because we start from 1 in the other figures. Okay, so in every odd round, we are going to have an end call. Right, round 1, round 3 are going to end. We're going to have an end call, and the nodes in every even rounds are going to be the votes. And here I want to mention, I told you before that it's a very easy way to switch between partial synchrony and the asynchrony. And basically, the main difference is that in partial synchrony, these end calls are going to be a priori known. Like, just think of like this for simplicity a round robin. Like, we just keep round robbing, and if we know in advance in every round who is going to be the end call, no need for communication, we just know, we agree in advance, right? This is going to work for partial synchrony, and for asynchrony, we are going to use some randomness that will come for a future round in order to determine the end call of a previous round. So that's basically the main difference between the asynchronous BFT on top of a DAG and the partial synchrony protocol on top of a DAG. Okay. What else? Yeah. So the goal is going to be, after we have our end calls in our well-described in a partial synchronous version, so we a priori agree on them, we have them, and we first want to agree which end calls we are going to order, and this is the hard part, and after we do that, the rest is trivial. We're just going to deterministically order their causal history, like going one by one. Okay, that's kind of a spoiler, but let's see how we are going to do it. Okay, so first the commit rule. Like I told you, the votes in every even round is going to, nodes in every even round are going to be the votes. And the commit rule is very simple. We need, a node votes for the end call if there is an edge between them. All right? So, and the commit rule says that if an end call has f plus 1 votes, so the end call can be committed. So in this case, we only have one vote, right? There is only one node that links to the end call, so we cannot commit A1 here in this example. However, we can commit A2 because we have 3 votes. See, 3 edges to the end call. Okay. Now that's tricky. That's not that simple, okay? It's a simple protocol, but not that simple. Because what can happen is that, I remember, like slightly different views of the DAG the validator have. So one validator can actually see this node, while this is like validator 1 doesn't have this node, so it did not commit end call 1. Another validator 4 in this example, does see this vote, right? Slightly different views of the DAG. Eventually, this guy is going to see this node, but it's going to be already too late. Okay, so and in this example, validator 4 actually committed A1 because F is 1, right? And we need 2 votes to commit, and A1 is committed. So we need to be really careful here and make sure that when we go and order the end calls, everybody are going to order the same end calls, the same order. So validator 1 has to order A1. even though he did not commit it directly, because when he was interpreting this round, he didn't see enough votes. Okay, so of course, like, we don't know a lot of tricks in distributed computing and consensus. It's most of the time it's quorum intersection, and we are going to use quorum intersection this time as well. And luckily, Rafael explains, like in his talk, what quorum intersection means, right? If you have two quorums and they are big enough, you have intersection. If they are big enough, you have one honest in the intersection, right? That's and one honest will never do contradicting stuff. You kind of rely on it, so you cannot achieve two quorums saying contradicting things. So in our example, we have f+1 votes to commit. And each node refers to n-f nodes from the previous round. So because we have in total 3 f+1 nodes, so in the intersection of these two, we have at least one node. And usually in Byzantine agreement, we need f+1 because f can be bad, but in our case, as we established, that nobody can lie, right? There is no equivocation, so even one node is enough for us. Okay, so with this in mind, and I'm going to demonstrate it with a figure in a second, if an anchor A is committed by some validator is in a local view had enough votes and committed anchor A, then all future anchors will have a path to at least one vote for A, and all future anchors will have a path to A. So in the figure, you see this anchor A2, he has to link to n-f 3 in this example nodes. He already links to 2, he needs to link to another one. And it doesn't really matter which one out of these two, he's gonna link to a vote, right? And if he links to a vote, by definition of a vote, there is a path between A2 to A1. And this is basically true to every node in this round, right? Same argument apply. And then inductively, we can easily prove our claim that every future anchor will have a link to A1, right? Okay, so this observation is important, and the opposite of this observation, if there is no path for a future anchor A prime to A, then no validator, when he was locally interpreting with DAG, could have committed A, right? Otherwise, by what we said just in the previous slide, there would be a path, right? That's just the opposite. Okay, cool. So with this is basically all we need in order to explain Bullshark, at least the partial synchronous version of it, in one slide. And this is what I'm going to do now. This is a local view of one of the validators, and he is going to take this and alter it, right? So this is how it's going to work. First, he checks if it can commit A1. Again, he cannot. There is only one vote. We need f+1. We need 2. Then he tries to commit A2. It doesn't even have A2, right? This is how it happened. It's like, right, A2, we are moving with n-f is enough to move forward, and it happened that we don't even have A2, and we move forward, right? So, but A3, we can actually commit, because we have 1, 2, 3 votes. So we commit A3. Now we need to go back. Remember, we need to make sure somebody could have committed A1, so we need to check whether we need to commit A1 or not. And we are going to use the previous slide's observation, and we are going to do the following. If there is a path between A3 to A2, we will order A2 before A3. But in this case, there is no path, so we are not going to order A2. However, there is a path between A3 to A1, meaning that we need to order A1 before A3, and the reason is because somebody could have commit A1 when he was interpreting this part of the DAG, right? So we have to do it. And note that it's not necessarily true that somebody have committed A1. It's possible that nobody committed A1, but it's still safe to order A1 before A3, and the reason is because, remember I told you that if we all have this node, then we are going to agree in our local DAG, the causal histories of this node in our local DAG is going to be exactly the same. So when we are in the process of doing this, right, interpolating the DAG, we look at our own DAG, and we are like, what we are doing now is like checking the causal history of A3, we're all going to agree on the same causal history, so we are going to apply the same deterministic rule. If I came to a conclusion that I need to be, if in my DAG there is a path between A3 to A1, then in everybody else's path there is also a path between A3, from A3 to A1, because this is like how we build the DAG. We agree on the causal history, right? So this is like a call property here of the DAG that help us like alter it. Okay, so after we do that, we need to recursively continue. We take A1 and we need to check whether there is a path from A1 to previous anchors and so on and so forth until we reach an anchor that we previously committed, right? Because we keep doing it. As the DAG grows, we keep altering it. And in this example, round 1 is the first round, so we don't need to do it. We just started from here. Okay, now after we did this, we need to go and causally history the entire DAG. So far, we agreed on the anchors perfectly, and we all agree on the validators. Now, the rest is like very easy. Again, the causal histories are the same. All we need to do is to apply some deterministic rule and all the causal history. Because so in this example, A1 doesn't have anything, so A1 just comes first. And then we take the causal history of A3, apply any deterministic rule you want. Again, everybody agree on the causal history. Doesn't matter what deterministic rule, they will come up to the same conclusion and exactly the same perfect order of the blocks. And that's basically our goal, right? We wanted to take this, we wanted to transfer it to this, and we wanted all the validators to agree, and that's the entire Bullshark protocol. Okay, so Bullshark has actually a few. So I wanna check if there are some questions before I go. Yeah.
So I'm still trying to grasp what you're saying, but for each little green square, you have transactions within that, right? Like A1 has transactions in it.
Yeah, the white ones is also have transactions. Each node has transactions, yes. Not transactions, metadata, right? The proof of availability, not really the data, the metadata.
Okay. I'm still trying to understand, like if I send a transaction to this system, how is it ultimately ordered?
If you send a transaction in the system, you have your validators, right? And the validators, they'll get their transactions. Right? So what they're going to do is they're going to batch them inside some batch. They're going to disseminate them to everybody else. They send the data. Like in this protocol I showed before, everybody else are going to persist this batch. They're going to send me a signature for this batch. I'm going to accumulate a certificate for this batch. And then I'm also, a separate mechanism, I'm also building the DAG, right? So I'm going to take this certificate and I'm going to inject it to one of the nodes, depending on where I am in building the DAG. Let's say I'm here, so I'm going to head it here. I'm going to put the proof of availability in the DAG. Then we are going to order all the DAG, and then I'm going to execute this one by one, and this will contain the metadata. In a good case, most of the time I will also have the data, because if I'm honest, I actually send the data to everybody else. They should have it, right? So in the best case, I never even need to go and ask for the data. I'm just going to execute the data. But if I don't have the data, I'm going to check the certificate, and I'm going to check who signed it. And then I'm going to ask them for the data. So you can think of like creative protocols. You can ask everybody, if you can ask one and then retry, whatever you want. But it's guaranteed you're going to get the data eventually, because they promise to have it, right? So they're going to reply.
So maybe the question I'm asking is, how do you choose how to order the metadata?
That's what we're doing here. This is like the protocol I described. We had this, right? And this is exactly what we're doing. First we agree on the order first we agree on the anchors. We have committed them, right, the anchors in the previous slides. And then after we agree, let's go back. So we go by A1. We cannot commit A1 because they have this commit rule, right? And then we commit A3. Then there is mechanism to actually check whether A2 or A3 had to be ordered first. And we came to a conclusion that A1 has to be ordered before. And now it's the...
This is like causal ordering, right? But
yes, this was causal order, yeah.
Within A1, we have like a list of metadata that is like mapped onto transactions that aren't shared, right?
Yes.
And so how is this list ordered?
Inside the list? Oh, that's, let's say, whatever you want, but the simplest thing is for the validator just decide and give you the list. That was your question all along. I am so sorry. I just went for, yeah. Yeah, but you get it, right? Like just the validator will just decide, yeah.
So different validators can have different rules for how they order this metadata.
Yes, yep. But it doesn't matter, right? Once they order it, everybody are gonna agree on the order, right? Yep. Yeah, you can do smarter things, right? You can do, for example, you can, after you order all the metadata, you can say, I wanna get the data for like, I don't know, five nodes. I wanna look at it, I wanna apply some deterministic rule, and I wanna reorder it, right? You can do other stuff. It doesn't necessarily needs to be this way, right? As long as everything is deterministic, you can apply any deterministic rule, right? Mm. Yeah.
I understand the point that, like, in parallel, there are transactions getting committed to those nodes, and then you order them, and then by ordering some transactions become embedded, because like maybe you submit to different validation.
Yeah, that's called duplication. Yes, that's a good point. If it's possible that the client is going to submit the same transaction to validators, and then we are going to end up ordering the same transaction twice, and what we need to do is discard one of them. Again, deterministically, we can discard the second one, right? And yeah, but that's a good point because it's actually, if everybody is going to do it, like I guess somebody will ask this question eventually, if everybody are going to do it, then it's going to harm our throughput, right? Because our real throughput will need to divide by the number of like not duplicated transactions there. Yep. No, wait a second. Yeah, I want to, yeah.
Okay, I'm not sure if I understand. So you said so there's going to be causal connection between some things. Then we know, okay, this has to come after the other. But aren't there going to be many cases where you have two things and there is like you can order them either this one or like there's no connection, right? So what do you do? Okay, so I mean, in round 3, right, you have 3 green.
Yes. How are they? Okay, sure. Let's see an example. So we decided to do this, right? First order A1, then order A3, right? Then now we need to order all the causal history of A3. Here's a simple rule for you. I'm gonna go, I'm gonna check all the nodes in the causal history of A3 which haven't been ordered yet. It is like basically this, basically all. Oh, well, what is going on here? Basically all these nodes, right, in this green square, right, all these nodes in the causal history of A3. And then one simple deterministic rule, I'm gonna go round by round and validator by validator. I'm gonna order this, then this, then this, then this, then this, then this, and so on. Does it answer does it answer the question? But because we all agreed on this is our end call. We all agree to first order this one and then order this one. So and then after we did this was the hard part. Now it's basically just applying deterministic rules. Like we're all gonna go see the causal history of A1 and deterministically apply it. Then gonna go see the causal history of A3 and just yeah.
Okay, so we agreed that A3 is now going like everything is going to be ordered by A3. That's what we agreed on, right?
Yeah, everything that wasn't ordered before, because at the beginning yeah.
So there's like a main, I mean, this is just, it's sort of like a main chain kind of thing.
What do you mean by main chain?
No, I mean, there's just one block by which we order everything and everybody orders by this one block.
Yes, exactly. And so exactly. So first we agreed on this one block and then we use it in order to order all the rest. Yeah, still have the question?
Yeah, I was thinking about like people trying to game the incentives here, right? If people have like particular ordering preferences, you said in a partially synchronous model, the leaders or like the anchors are selected in advance. Yes. People can send their transactions particularly to them because they want a particular ordering and they know that this node is going to decide the order. And then in the fully asynchronous model, you said the anchors are decided in retrospect.
Yes.
And so as someone that really wants my transaction to get in or my metadata to be ordered particularly, don't I have an incentive to like spam all the validators or do something there to like game either to game the deterministic rule that you just talked about, the pre-agreed deterministic rule, or to try to maximize my reach to the anchor?
so there are two things here. So first, everybody has transactions. So anchor doesn't really play any special rule here. It's just a way to order it. So they're all symmetric. But what we said is true. If I want my transaction to go as fast as possible, I will probably send it to everybody else, right? So orthogonal to this mechanism, we need to make sure we need to disincentivize them not to do it. Yeah, this is like this is hard. And this is orthogonal to, like, not in the scope of this talk. Yeah, it's so hard that I'm not even like there is not a clear solution to that. It's the hard problem. Yep. Yeah.
Yeah. So if I'm understanding correctly, once we've agreed on A3, every block that's a path to A3, we can then order those based on deterministic. But how do the parties know that there is a path to A3? Like, does A3 contain a record of every?
Yeah, exactly. Each node here contains a reference, yes, to the previous nodes. That's
But would you need to contain a full history?
No, just references for n-f nodes in the previous round, and then if you look at and then like recursively, right? And then you link to these guys. This guy links to this guy, so you build your DAG. All right. So, okay, let's move forward. I think I have 10 more minutes. That's good timing. Okay, so a few properties. Again, Rafael mentioned chain quality. So in these DAGs, we basically get chain quality for free. At least n-f nodes in each round are honest nodes. And at least n-f nodes in each round are gonna be added to the total order. At most F are Byzantine, so we get at least half of the nodes are gonna be honest, and this is actually proved to be optimal. And we also have fairness and garbage collection. By fairness, I mean that even if we have these validators, which is like super slow because it's like poor guy in Australia, like always late to the party, they always like move forward without him because they need only n-f to move forward. And they never fast enough to be included in these like links, which we call in these like links that are used for consensus. So for that, we have weak links. A weak link it's not used for consensus. It's like the previous slides. It's ignored completely in consensus. Not in consensus. It's ignored completely in ordering the anchors. It's only used for the causal history. If you have a weak link, you're going to be considered as part of the causal history. And once the next anchor here is going to be ordered, you're also going to be ordered. So just a very simple mechanism. And one word about garbage collection, because if you have a round-based DAG, together with consensus, like garbage collection becomes like really trivial. And before previous DAG constructions, they wasn't based on rounds, and garbage collection was actually like one of their drawbacks. I think one of the reasons they weren't adopted. So here, because we have the rounds, garbage collection is basically trivial. What we do is that every node you include a timestamp, and then you compute the timestamp for a round by a median of the timestamp in the node. That happens once you come to order the causal history of A, right? You compute the timestamp. For each round, the anchor gets the timestamp of the one round before. And then you pick a number and you say all the rounds with timestamp like smaller than the anchor's timestamp minus delta, I'm gonna garbage collect them. That's as simple as that. Very like trivial garbage collection. And the way it works together with fairness is that this poor node in Australia, he cannot be too slow, right? He needs to be fast enough in order to be added to the DAG before the round is garbage collected. Like after I garbage collected round one, if the validator's nodes come later and I already decided to garbage collect it, I'm not going to accept it to my DAG. But if it comes before, I'm going to accept it, I'm going to add a weak link, and it's going to be ordered. So as long as you are not too slow, your nodes are going to be added to the total order. Okay, so to conclude, I hope I convinced you that the protocol is extremely simple. As you saw, no view change, no view synchronization. zero communication overhead on top of the DAG, just need to build a DAG. You get chain quality for free and some sense of fairness together with the garbage collection during like synchronous periods. Okay, so I haven't talked about Liveness, and I do want to say a few words about Liveness. So I said before, and Aleph should be here as well because it's also an asynchronous protocol, but they use slightly different randomness. So I thought this is why I didn't include them to the slide. But yes, for asynchronous Liveness, what we need to do, and we need to have some randomness coming for the future round in order to, in retrospect, to elect the encore. And the easiest way to do it is some threshold randomness, threshold signature. You add a shell to every node, and you get your signature, you get your randomness. That's actually not that simple when you think about it, because if you need to reconfigure the system, then every epoch you need to come up with new randomness, and that's not actually that simple. But at least in theory, if you have randomness, you can easily solve asynchronous consensus by using this randomness to elect the encores in retrospect. Now, for the partial asynchrony, I told you that we need the encores to be predefined. Now, nobody asked, but this was the deterministic protocol, partial synchrony, no randomness, and somehow I achieved consensus, right? I didn't tell you where the timeouts are, right? I have to use timeouts, otherwise I'm circumventing FLP. And of course, there are timeouts. So, because what if I don't have timeouts, what can happen is that the adversary can play me in such a way that these encores will always arrive late, and I will never have enough votes for them. So we do have to have timeouts, and there are two options to use the timeouts. One, and which ended up more performant, is to add the timeouts directly to the construction of the DAG. I told you before that we can move forward whenever we link to n-f nodes in the previous round. Now I lied to you slightly, and now I will correct this lie. What we need to do is, if the encore is part of this n-f, I'm good to go. I can continue immediately. If the encore is not there, so I'm gonna give him a chance. I'm gonna wait for a timeout to receive the node from the encore. If I receive it, once I receive it, I move forward immediately to the next round. Otherwise, I do it whenever the timeout expires. So this is how we use the timeouts. And do I have time? Maybe, yeah. So the other approach that we considered, and at the beginning, this is like another example, like you have a cool idea that didn't work in practice, is that we thought, oh, we can do something smart. We can separate the physical DAG. We can continue like building the DAG asynchronously without all these timeouts as before, and we can piggyback a logical layer of the DAG on top of the physical layer of the DAG and use the timeouts there. So once in a while, I'm gonna say this physical node is also a logical node. I'm gonna put a bit over there, and then I'm gonna, when I interpret the DAG, I will only consider logical DAGs. And yeah, I thought it's smart, but at the end, when we implemented it, it was too much overhead to build it. Like the physical DAG went too fast, so like a lot of resources, like a lot of storage, networking, like a lot of threads, like yeah. And actually, it's actually good to garbage collect your things, not to garbage collect, to back pressure your DAG for the best performance. So we ended up with this approach. All right, so where we are in the conclusion. I just wanted to point out all the papers are online. You can go there. There is also a blog post that's this talk is basically based on this blog post in decentralized thoughts. You can go read there. And yes, for the last slide, I wanna say the following. So I hope I convince you that consensus is no longer a bottleneck. Remember this like consensus execution storage. Consensus is much faster than execution and storage guaranteed now, and we have like much bigger bottlenecks in the system. Yeah, otherwise we were already, where is Lara? We already beat like Visa like long ago, because consensus can do much more than Visa, but unfortunately blockchain is not only consensus. So consensus is no longer the bottleneck. So what is the next for BFT, right? I told you focus on crypto, but still if you wanna insist to work on BFT, so what is there to do? So one thing is incentives, which is people are overlooking it now. They are like, everything just works, right? We just, okay, we have some incentives, they are not perfect, and things works, right? But I believe that if blockchain here to stay and to really be adapted, we will need to add incentives to every part of the protocol. Like otherwise, people are gonna manipulate it in every possible way, right? So we have to have incentives, and this is a very hard problem. I briefly said that randomness is not easy because we need to generate randomness. Of course, if we could do one trusted setup once, we could had randomness forever, that would be perfect. But unfortunately, we need to reconfigure the system, we need to bring new validators, we need to remove validators. Every time we need a new randomness, we need efficient protocols to bootstrap randomness. And the biggest question of all is sharding. So I mean, I think that the expert on zero knowledge here will probably disagree with me, but based on the numbers that I see today, it's not even close to to be to where we want the blockchain to be. If we talk about millions of transactions per second, at least not in the near future. I don't see how we achieve it with ZK rollups. So we need some sharding mechanism, and we need to invest more research there and more time and thinking how do we do it properly. And that's not only an engineering sharding or problem or research problem. We don't even understand the problem because nobody really knows what the workload is going to look like in 2 years, right? If we knew that we can easily separate from different namespaces, right, we can do sharding easily, but we cannot do, we don't know that, right? We don't know how it's going to look. So how many cross-shard transactions we are going to have, we don't have enough data yet. So this is a really, really hard problem that, yes, people need to pay more attention to because, yeah, that's the future. All right, and thank you very much. I think I am on time.